Good evening, everyone, to this session of Astro Adda, series of talks organized by the Nehru Planetarium, Nehru Memorial Museum and Library, and the Public Outreach and Education Committee, Astronomical Society of India. Today, we are gathered to celebrate a Cosmic Dhanteras. So, aspects of our understanding of dense celestial objects in which in some sense are connected to production of many of heavy elements, and in particular I think our speaker we have with us Dr. Sushan Konar, who has worked at the Raman Research Institute at the National Center for Radio Astrophysics, and um, has had a very long experience of working with these dense celestial objects. And though we did not ever directly collaborate, Sushan, but I have been kind of very interested in the work related to dense celestial these objects, in particular neutron stars, which you have been doing for a long time. And we look forward to you taking us through this presents, this cosmic Dhanteras. So let's see what all gold we can extract out of this. I'll add your presentation, and when you start, you could go full screen. I just something to tell all the viewers. Those of you who are regulars, you know that the speaker would not be able to see your chat comments till the presentation is done. But you can use it to put any of your questions in text. So use the text box for all your questions. And Sushan, I'll hand over to you.
Thank you very much. Let me begin by thanking Ratnashri, whom I have known for a very long time now, for arranging these talks and asking me to be part of this program today. And I thank all the listeners who have taken out the time on a Saturday evening to listen to this. I will now start my presentation. So the title of my talk is Cosmic Dhanteras, which is a bit appropriate. Only last week we had Dhanteras, in which traditionally in India we celebrate the heavy metals, in particular precious metal like gold, etc. And one wonders why one would like to celebrate such heavy metals, except for the fact that they are bright and shiny and look very nice. And they also have many interesting properties which allow us to use them for very interesting applications, apart from being made into jewelries. Actually, what makes them special is also their rarity. For example, gold is not as easily available or is as plentiful as something like iron. And as we progress through the lecture today, we will see why that is so. It's not an accident that such metals are much rarer, and how they are produced. The answer to this question is only now becoming clear to the scientist. So we would try to take a look at what all we understand at the moment about these heavy metals. So let's first begin with the elements, and let's try to figure out what are the most abundant elements that we have around us. For example, human body. Now, all of you know that human body consists about more than 60% of water. Now, water has 2 parts of hydrogen and 1 part of oxygen, but if you go by weight, then it's only 2 units 2 mass units of hydrogen and 16 mass, actually, 16 mass unit of oxygen. So therefore, it is 8 times more abundant than hydrogen in one molecule of water. So now if we do our maths a little more carefully, this is what we have. In the human body, oxygen is actually 65%. And then you have carbon 18%, hydrogen 10, about 10%, and various other uh, material. And you notice that there isn't much of heavy material in this. Of course, we do have some heavy material, heavy metal in our body because we inhale the motor vehicle exhaust, and that usually contains many heavy metals like mercury and so on. So we do have some trace elements of heavy metal, but in general, human body doesn't really have too much of heavy metal. Now, for example, if you want to consider other objects that we see around us, what do we have in them? Say, for example, the walls of a room that you are sitting in or I am sitting in. They are mostly made by concrete, which is mainly made by sand, which is silicon dioxide. And so there again, you will see that you basically have a lot of oxygen. So it shows you that there are a lot of oxygen around our everyday life. But now we come to the digital world, and we are all using cell phones and computers, without which it would not be possible for me to give the lecture today, or for you to listen to the lecture today. And see what we have in a smartphone, for example. And you immediately see that there is considerable amount of gold, which is 0.02%, not too bad. But on the other hand, if you look at the price, it's 72% by price. So that's why the smartphones are so expensive. So, and now you will see that in a smartphone, what you have is these 3 elements, which have been marked with red lines. Except for those, all of them are heavy metals. And these metals are precious. They're not produced in the universe too much. And even on Earth, we do not have a lot of them. Now, if we look at the abundance of elements in the universe as a whole, what would we see? For example, these are 2 beautiful nebula, Elephant Trunk Nebula and Horsehead Nebula. Both are star-forming regions, which means that young stars are forming there. There is a lot of dust and gas. And how do we figure out what is the composition of the gas and dust and the material there? The standard and the most robust way of finding the composition of stellar objects or a region in the sky is to look at the spectra of the light that is coming from that region. If you look at the spectra, either in emission or in absorption, you know what is the signature of a particular element. And if you can compare your laboratory spectra to the spectra that you are obtaining from the sky, then you can clearly identify what is the material, what is the element from which you are getting the light, and then you can figure out the abundance of the elements in the universe. Now, this way, scientists have estimated the abundance of the elements in the universe, and here is it. And you see what we have. Now, hydrogen is 75% of all the material that is there in the universe. Helium, the next element in the periodic table, is 23%, and everything else gives you just 2% of all the material that is there in the universe. So what astrophysicists do, they do a very interesting and clever way of putting their periodic table, and it looks like this. You have hydrogen, you have helium, you have few other metals. In fact, in astrophysical parlance, beyond hydrogen and helium, everything is called metal. Of course, if you try to use that definition in real life, you will get into trouble. But nevertheless, in astrophysics, that's what everything else is called. And you notice that there are only a few elements which are there in this periodic table, because the abundance of everything else is really, really negligibly small. So now, as I said before, that if you look at the spectra from a region of the sky and then compare it with the laboratory spectra, and then you can figure out what are the elements that you are getting the light from, how can one be sure that we know about all the elements that there exist in the universe? That is because we have this periodic table, which was first made by Dmitry Mendeleev, a Russian chemist, in the year 1869. Now, you notice that this is Mendeleev's original periodic table, and instead of the tabular form that we are familiar with, he put them as columns, and he put down all the elements that was known at that time, and he ordered them according to their atomic numbers. Now, if we cast this table in our familiar form, it looks like this. Now, two aspects of this table that one should note. One is obvious, that there are gaps there. There are holes in this table. Why? Because those elements were not known in Mendeleev's time. Now, why is that so? That is because the elements that should be sitting there exist no stable isotopes or long-term stable isotopes of these elements, and that is why these elements were not found naturally and were not obviously not known, and that is why they do not appear in Mendeleev's table. The second aspect which you should notice is that many of the elements have a number which is fractional. Why fractional? Because that the number corresponds to the mass number. The fractional number basically signify that there are other isotopes, and the different isotopes occur at various ratios, and when averaged over those isotopes, that is the average mass number that one finds. Now, when we talk about isotopes, we know that for an element, different isotopes have the same number of Z, that is protons, but different number of neutrons. And it is possible for an element to have different number of neutrons and therefore have different isotopes. Now, is there a limit to how many neutrons a particular atom can have? Yes, there is a limit, because if the ratio of neutrons to protons exceed certain value, then it becomes difficult for the nucleus of the atom to hold on to the neutrons, and then what happens is some of the neutrons break free from the atomic nucleus, which we called a neutron drip. Now, only recently, scientists have figured out the neutron drip line for fluorine and neon only last year. Till then, we only knew about the neutron drip line till oxygen. So, as you see that even though we know about these elements from antiquity, and the science of chemistry is reasonably ancient, but still there are aspects of the properties of these elements that only now we are learning about. Now, as I said, that there has to be a particular ratio between protons and neutrons for an atomic nucleus to be stable, and you see that this is a graph where in the x-axis you have the atomic number, that is the number of protons, and in the y-axis you have the number of neutrons. And this line is the 1:1 neutron to proton ratio. And the cyan band is the band of stability for the terrestrial atomic nuclei that we know about. And you see that in the beginning, the ratio is about 1:1. Then later it rises a little, but it does not go very far away from the 1:1 line. On the other hand, in the astrophysical situation, in particular the neutron stars that Dr. Ratnashri was referring to, there we have some very peculiar atomic nuclei very far away from the band of stability. For example, tellurium, strontium, molybdenum, which have many more neutrons that an atomic nucleus on Earth can have. We'll talk about that a little later. So, what happens if we have too many neutrons? Then the nucleus becomes unstable and it goes through radioactive decay. Now, there are various ways of this radioactive decay. I'm sure you have learnt about many of these. For example, there could be alpha decay. Alpha particle is nothing but the nucleus of a 4 helium particle. And so, a parent nuclei can give away an alpha particle and then is left with an element which has its atomic number reduced by 2. And then there could be beta decay. Beta decay is basically a neutron inside the nucleus decays into a proton, an electron, and neutrinos, and that electron goes out, and therefore, because a negative charge is going away, the daughter nucleus now has its atomic number raised by 1. So there are various other processes through which the unstable nuclei can find a stable configuration. Now, of all these radioactive channels, the most important channels in the astrophysical context are beta decay, electron capture. Electron capture is just the reverse of beta decay, or spontaneous fission. Now, spontaneous fission happens when a nucleus become extremely neutron rich. There are too many neutrons in it, and therefore it cannot hold on to such neutrons, and it fissures into 2 daughter nuclei. Now, in astrophysical context, a nucleus becoming too neutron rich has a very great significance, and we will see that this is one of the processes through which these heavy metals, heavy elements are produced. So this is our modern periodic table, and I'm sure all of you know that there are various properties because of which they are arranged in a particular fashion, and the heaviest element that is naturally occurring is, of course, uranium at 92. Now, all these elements beyond uranium here a whole lot of them. These are all artificially made nuclei, artificially made elements. We have created them in the laboratory, and of course they are not stable. Had they been stable, we would have seen them in nature, but there does not exist any stable isotope for them. And only recently the element with atomic number 117, this is called unum septium, this has been confirmed to have been seen in the laboratory. So we are producing more and more artificial nuclei, but artificial elements, but none of these are stable. Now, let us try to look at the periodic table in a slightly different fashion. We have the same periodic table, and now this is an astrophysicist's periodic table, which tells you what is the origin of all the elements that you have. And you will clearly see that hydrogen, helium, and a little bit of lithium, these were created in the Big Bang, the beginning of our universe. And then there are various channels through which all the other elements have been created. And here we have these human synthesis, artificially synthesized elements for which there are no stable isotopes. And you notice that this magenta colored blocks, which signifies that these have been created in merging neutron star events. Now you see that all our precious metals, be it gold or platinum, etc., all have been created when two neutron stars collided and merged with each other. And many of you may remember that one such event was observed for the first time in 2017. It was initially observed through the gravitational waves that was generated at the time of the merger by LIGO and Virgo, and immediately it was followed up by various electromagnetic telescopes, and it was observed to have many interesting phenomenon associated with it. One of the processes that has been observed, and now it has been confirmed, that is the process of heavy element production. We will come to that towards the end of this talk, but please note that this is something which was not seen or understood as clearly before the observation in 2017. And very interestingly, even though the observation happened a little earlier, the day it was announced to the scientific community happened to be on the day of Dhanteras in 2017. So now let us go back and try to see how we got all our elements. So of course the universe started with Big Bang, and we would not really deal with I'm sorry, the cosmological aspects here, except to say that this is the time when the universe started, the time started, and it had initially, there were a lot of quarks, and at a time which is about 10 to the power minus 6 second after Big Bang, when the protons were formed, the protons and neutrons would be formed, and only after the protons formed, then we are starting to have elements being formed. Please remember that a proton is basically a hydrogen atom without its electron. So this is where the hydrogen is being formed, and this is the 75% of hydrogens that we see today. I mean, some of the protons will, of course, go into helium and rest of the material, but all the hydrogen that we see today are coming from this point of time. Now, initially, there were quarks, and these quarks, some of these quarks combined to make protons and neutrons. This happened when the universe expanded and cooled down a little. Only then the quarks went into bound states. Now, two up quarks and one down quark made into a proton, and this is the charge, 2/3 of an electron, positive charge, corresponds to the charge of the up quark, and down quark has a charge of minus 1/3 that of the unit charge. So you have two up quark and one down quark making a proton, one up quark, two down quark making a neutron, and thereafter we have the production of heavier elements. So once you have proton, you have hydrogen. Now we are producing heavier elements. So what happens? The basic idea behind nucleosynthesis, the basic nucleosynthesis that happens, it happens inside the stars, it happened in the early universe, is two protons and two neutrons get into a helium nucleus, and the mass difference comes out as the energy. Now, this picture is not really completely accurate. What actually happens is this. So originally, as I said, there are only protons. So protons are formed. So two protons join together to form a bound state of two protons. So it's a proton-proton bound state. Then one proton decays into a neutron, and then you have a proton-neutron bound state, because this phase is unstable. So you have a proton-neutron bound state, which we know as the element deuterium, which is basically a hydrogen isotope with one neutron. So you have a deuterium and a positron and some neutrinos going away. In the second step, deuterium combines with another proton and goes into a state which is PNP, which is a 3 helium, a helium atom with only one neutron. Then two such 3 helium combines to give the 4 helium, 2 protons, 2 neutrons, and 2 protons, that is 2 hydrogen ions, again are thrown out. So that is the basic nucleosynthesis that is happening in all the main sequence stars, and which happened in the early universe to give us helium from hydrogen. Now, after helium is created, new elements can be formed by combining helium with a proton or with another helium itself. So now the easiest thing to do is to combine a 4 helium with a proton. Now that combination is extremely unstable, so that doesn't really happen, so to speak. Then there could be various channels through which, various combinations through which you can have production of various elements like beryllium, like lithium, like boron. Now, what happens is neither beryllium or boron survive from the early universe nucleosynthesis because they are very short-lived. For an example, the half-life of 8 beryllium is about 10 to the power minus 17 seconds. So even though these are produced, we are not going to find anything today. What survives from the early universe is a little bit of lithium. And that's what we have seen when we saw the periodic table in which their origin was indicated. Now, initially, people thought that nucleosynthesis cannot take place inside stars. So there was a raging debate, and there are stalwart scientists who thought that the temperature in the cores of stars are not large enough for nucleosynthesis to take place. And it was Sir Arthur Eddington in Cambridge in the 1920s who first said that that is the place where nucleosynthesis must take place, because he said that one should then look for a place which is hotter than the inside of a star. Now, some close to 40 years on, the basic theory of synthesis of elements in stars was laid down by another person from Cambridge, Sir Fred Hoyle, along with Margaret and Geoffrey Babbage and William Fowler. You see in picture all of them. And this is Margaret Babbage, who was the last surviving member of Babbage, Fowler, Hoyle group. And she passed away earlier this year at the age of 100 plus. And she has actually seen the evolution of modern astrophysics through her life, and she has been a very significant member and had done extremely significant work for astrophysics to progress. And this is the paper. It's a 100-page paper that they wrote in Reviews of Modern Physics, which is still now considered to be the Bible of nucleosynthesis in stars. And some of you who might take up this subject, astrophysical nucleosynthesis, would definitely have to go through this paper if you do. So now we have talked about stars. So what are stars? How stars are made? So we know there are 4 fundamental forces, and gravity is the weakest of them. Then we have weak force, then electromagnetism, and finally we have the strong force. Now here their relative strength have been shown. If you take the strong force to be 1, you see that you would think that gravity would not be important at all. However, if you look at this column, you will see that only electromagnetism and gravity are long-range forces. Remember, both of these forces are 1 over r square, where r is the distance between 2 interacting bodies. So these are 1 over r square forces, and these are long range forces. Both weak force and strong force are effective within very short distances. So therefore, when we are talking about long distances, we are talking about huge bodies. Electromagnetism and gravity are the ones that are important. Then again, electromagnetism is important where in the regions of space where you have free charges. Now, most of the universe, larger bodies, when they become charge neutral, then gravity is the force that one has to reckon with. So astrophysics is basically all about the gravity and how other fundamental interactions are holding gravity off. So, as you have seen, that strong force binds nucleus, weak force is relevant for radioactive decay, electromagnetic force binds atoms, electromagnetic force also binds smaller objects like a human body. That is, we are not, of course, not gravitationally bound. But when we go to larger and larger objects, then we reach a point when the objects start becoming gravitationally bound. Here's a beautiful example from our solar system asteroids. You see, you have this asteroid with completely misshapen, longish shape is Eros, 5 kilometer by 15 kilometer. Then there is Phobos, 9 kilometer by 13 kilometer, roughly spherical. Then there is Ceres, which is the radius is 470 kilometer and it's very, very spherical. And all these asteroids of arbitrary shapes, they are known as the potato asteroids. Now, when a potato asteroid becomes gravitationally bound, then it becomes spherical, and that radius at which it transitions from being a potato to a sphere is given by this, where rho is the density of the material of the asteroid or what have you, and sigma is the uh, shear stress of the material by which the asteroid is made up of. So here you see that from a little bit of chalk or a piece of rock or human body, we are moving to a region in which it becomes gravitationally bound. So now, in the case of stars, which are gravitationally bound fluids, what is important is, for a fluid element, it should be in hydrostatic pressure balanced condition. Now, the equation for hydrostatic pressure balance is given by this: dpdr is equal to minus g m of r, where m of r is the mass contained within the sphere radius r, rho r the density of the sphere, by r square. Now, stellar equilibrium depends on a few other equations, which is given by the equation of energy generation, of energy transport, the equation of state, what is the pressure of the material for a given density and temperature, and the obvious mass radius relation. Now, if you have such objects, as they become larger and larger, the temperature at the core increases because of gravitational contraction, and you reach a certain mass at which the nuclear fusion starts. We know that there are big objects like Jupiter's, but they are still planets. One then reaches a size which is about 10 times the mass of Jupiter, at which the hydrogen fusion, the conversion of hydrogen into helium-4 starts. But there are objects which do not have adequate mass to complete that conversion, and it stops at deuterium. So it produces deuterium, and then the nuclear reaction doesn't go forward, and there we have the brown dwarf. Only when hydrogen to helium conversion can be completed inside an object, then only we call it a star, like our sun. So, as you have showed before, the stellar nucleosynthesis, that is going from hydrogen to helium, is similar to what we have seen in the early universe, and this way of converting hydrogen to helium is called a pp chain. But there is another way of converting hydrogen to helium, And that is called a CNO cycle, where we have carbon, nitrogen, and oxygen as catalysts. They are standby elements. So therefore, it is obvious that this is happening in stars which have been born after the first set of stars had uh, gone through producing all these elements. These elements then were spewed out to the interstellar medium uh, through a supernova or some such explosion. And because of that, the next generation of stars had in them a little bit of these heavier elements, and they could then act as catalyst. And so therefore, this is another way of having the same reactions but with a catalyst. So this is called the CNO cycle, which mainly happens in heavier stars. Now, stellar nucleosynthesis can go on from hydrogen to helium, then to beryllium, then to carbon-12, etc., and so on. Now, when all these fusion reactions are happening, when I go from hydrogen to helium, the mass of a helium nucleus is less than the mass of 4 protons that we started with. And therefore, this mass defect, this little bit of mass that has been lost, this comes out as the energy, and that is the energy which the reactions produce. So these are called exothermic fusion reactions. So there is a reaction and therefore you get some energy. But if you look at the baryon number per nucleon inside a nucleus for various elements, you see that iron 56 sits at the bottom of this curve, which means that if you want to fuse iron, you do not get energy, but you have to provide energy. And that's what happens in massive stars after they have formed iron. So what happens in the final phases of the life of a massive star? Now, before we go into that, let us just quickly take a look as to what are the end states of various gaseous configurations that we started with. First of all, if we started with a mass less than 80 times the mass of the Jupiter, these are failed stars. They didn't become stars. So when the mass is less than 13 m Jupiter, no fusion reaction happens. So these are giant planets. Between 13 and 80 mass of Jupiter, the nuclear reaction starts, but it goes only up to deuterium generation, and these are the brown dwarfs. Now the stars where the full hydrogen to helium reaction can happen leave behind stellar remnants after their lifetime is over as white dwarfs, neutron stars, and I'm sorry, black holes. Now we would not definitely talk about black holes in this lecture, but we would mostly concentrate on neutron stars. Now this is schematics of which stars would leave what kind of remnants. Obviously, when you start with a main sequence mass of 0.08 to about 8 solar mass, it goes into, after main sequence, it goes into a red giant phase, then a planetary nebula, and then a white dwarf, the mass of which is less than the Chandrasekhar mass. Similarly, between 8 to 25 main sequence mass goes into a blue supergiant, a supernova, and a neutron star. And then if the mass is larger than this, then it ends up as a black hole. Of course, depending on the composition of the initial material, there would be various differences, and these numbers are, of course, not very stiff. There would be huge uncertainties depending on the compositions and various other issues, presence of binaries. So there are very many factors, but this is a very rough idea of how the stars would end up as. So in the late life of a massive stars, what we have is the star finishes hydrogen burning in the core, and then it starts to proceed burning helium in the core region, and the outer region still burns hydrogen, and so on and so forth. So a phase comes when we have an onion shell like structure. At the center, there is iron, and then there are various shells of uh, lighter and lighter material. And this phase is called, this configuration is known as the configuration of shell burning. This is a late life picture of a massive star. Now, when iron has been reached, as I said, the fusion reaction is no longer exothermic, it requires energy. So then what happens is, but there are still a lot of uh, neutrons and protons floating around in the region, in the core region where uh, iron has been generated. So there are various kinds of processes that can go on, and these are called nuclear transmutation. And there are two main processes. One is called the S process, very cleverly known as S process for the slow process, and there is one R process, which is basically the rapid process. So what is a slow process? What happens is, here is an example. An element, a nucleus, captures a neutron, and then it undergoes a beta decay. Now, please remember, when a beta decay happens, it is a weak interaction, and therefore it happens very slowly. So, therefore, a material can capture a neutron, then undergo a beta decay, then it immediately, its atomic number increases by 1, so it becomes another element with the atomic number increased by 1, and then this process can go on. This is called a slow process of nuclear transmutation, which may happen in late phases of stellar evolution in the supernova. And there is this called R process. What happens in R process is, again, there are a lot of neutron capture, but now there is lot of neutron capturing one after another, and then there is no time for beta decay. So what happens is, now is that you have extremely heavy isotopes of elements being formed, and then at one point there may be very rapid beta decay to generate a completely new element which is much higher in the atomic number. So now let's again get back to the end products. Now, for a white dwarf which has an average density of about 10 to the power 9 grams per cc, it's like a crystalline solid of heavy atoms, but only up to iron 56, which is immersed in a sea of Fermi degenerate electrons. Now, what happens for white dwarfs is that in an ordinary white dwarf, you do not have exotic material only up to heavy atoms, only up to iron 56. What happens is, if this white dwarf is in a binary and more material is accreting onto it, and the mass gets exceeded over the Chandrasekhar mass, it could explode, or some such process can happen. And only when that happens, then we have newer elements, heavier elements formed, and those we have already seen in the periodic table that some elements come from white dwarf explosions. Now, we get neutron stars, as I have shown, from much heavier stars, and this has a neutron star typically has an average density of 10 to the power 15 grams per cc, which is it's like it's the nuclear density. So it's basically like a huge single nucleus, but that is not all. It has a small bit of outer crust in which there is a solid exists. But what happens is, in this solid, the material is very weird, and the nuclei are extremely neutron rich, the kind of nuclei that you would not see on the terrestrial situation on Earth. Such neutron rich nuclei exist in neutron stars because of the extremely high density in which such neutron rich nuclei can be stable. And even there, when the density exceeds about 10 to the power 11 grams per cc, the neutron richness becomes so high, some of the neutrons drip out of the material. So then there is something like it's a solid with some electrons and plus some free neutrons floating around. So neutron star is really going into extremely exotic material, very neutron rich nuclei. And of course, inside the neutron star, that's the bulk of the neutron star, which is for it's for a 1.4 solar mass neutron star, the mass of the crust is about less than 0.05 solar mass. So the bulk of the star is basically 90% neutrons and about 10% protons, and that gives rise to very interesting possibilities later. So this is a schematic diagram of the neutron star. We have this outer crust and inner crust, as I have talked about. Ignore the superfluidity, superconductivity part, which is not the topic for today's lecture. And here is something interesting that I wanted to show you. This is a composition of the neutron star crust, and the nucleus that is most stable at a given density. So what we have here is the density and the stable nuclei, the most favored stable nuclei in the neutron star crust, and corresponding nuclei on Earth. Of course, you please remember that when I show the corresponding nuclei on Earth, I am not saying that it corresponds to these densities. So these densities only correspond to the neutron star crust. Now you see that you are getting very weird nuclei with hugely larger neutron number compared to the elements on Earth. For example, if you look at this element, even on Earth, it already has too many neutrons. But you compare that to the object we have on the neutron star crust, it has really very large number of neutrons. So it's arbitrarily, weirdly neutron rich elements that we see on the neutron star crust, and that is there simply because of the pressure conditions that are seen in the neutron star crust. Now, again, in the base of the neutron star crust, the material becomes the pressure conditions become so extreme that nuclei are no longer even spherical. They take up various disc and rod shapes. They are known as the pasta phase, but basically you have a huge number of neutrons there. So now, if we have two objects, two neutron stars, which are already very weird, very unusual inside, if they merge, then what happens? This is a schematic diagram for neutron star merger. So there are two neutron stars, they are in spiraling, and they merge, and there is a phase of gravitational wave generation. Then there is a viscous phase, and there is a spin down phase. So now all of these phases, they could most of the scenarios in most of the scenarios, they would sort of end up as a black hole, or sometimes it may end up as a stable neutron star, depending on the mass and how much mass has been expelled out and so on. So if we look at it in a different fashion, what we have is there is this marged object. So here it's being shown as a marged object, and a lot of material goes away in jets and so on. There is this ejecta, this material which is ejected out. Now, where is this material coming from? This material is coming from inside the neutron stars. Remember, these two neutron stars already had the interior composition that we have talked about. Now they collide, they merge, and material from inside the neutron star is now being ejected out. So what do we have? We basically have a huge number of neutrons and nothing else. Okay. So what happens is that all these neutrons, they come together, they form something, some bound object, and immediately there are decay channels through which some of the neutrons decay. Please remember that free neutrons have very short decay time. They exist stably inside a neutron star because of the huge pressure that is realized there. So immediately the neutrons would decay and would create bound objects, which are various heavy elements, and from there we would get all these extremely heavy elements that we have been talking about. Now, there have already been detection of such heavy elements. For example, the 38th in the periodic table, strontium, that has been clearly detected for the gravitational wave event 1708-17 that I have talked about initially, and that clearly shows that heavy elements have been produced in this neutron star merger. Now, we also know that heavy elements are produced in supernova when a massive star explodes and leaves a neutron star, perhaps. So now there are these two channels which are talked about in the context of production of heavy elements. Now, there are two aspects one must remember: the time scale, the frequency of the events, and the amount of material which is produced by these events. So a DNS merger, double neutron star merger, happens once in about 10,000 years, whereas a supernova happens once in 100 years. On the other hand, a DNS merger produces heavy elements, of the amount of the mass equivalent to the Earth, whereas a supernova produces mass about 1,000 times less. So therefore, if you have a supernova explosion that also produces these heavy elements, so supernova events are much more, but they produce less amount of material. On the other hand, double neutron star merger events are much more infrequent, much rare, but they create much larger amount of such heavy material. So therefore, it is understood that we should see clumpiness in these heavy materials, the clumpiness in the abundance of heavy material in the universe. Now, as I have said, our body chemistry does not have a lot of heavy elements inside us. As you can see, this is from exploding massive stars. That's most of our body, and then from dying loma stars, and from Big Bang nucleosynthesis, and so on and so forth. So we do not have these blue things inside us. These blue elements which have come from double neutron star merger are there in only in heavy elements, which we can go and look for their signature in the primordial rocks and such like. Now that has now been done. Scientists have looked at various rocks, and the decay, if you have heavy material and you have very heavy radioactive material, one can look at the decay products of such material. And people have gone and looked at primordial rocks, and they understand that there have been a double neutron star merger in the solar neighborhood about 10 to the power 8 years before the solar system was born, because that material is the primordial material sorry, from which the sun and all the planets have been made up of. So therefore this is now understood that about 100 million years ago, 100 million years before the solar system was born, there was a double neutron star merger in the vicinity, where about 1,000 light years away. So now one tries to think that okay, perhaps we then know where such a thing may have happened, but that is not very easy. First of all, we do not have any directional signature from such studies. We only know that it has happened that distance away, but in which direction we do not know. And also the solar system has been going around the galaxy throughout its life, and not only in this plane, but it also there is an undulation over and above this apparently planar looking motion. So therefore the solar system has also been changing its position. So the scientists now are trying to figure out how how one can really pinpoint where the DNS merger happened, from which we probably inherited all our heavy metals. There is one more important issue related to DNS merger. Now, there has been a recent study in which people have looked at the habitability of various exoplanets. You know that the exoplanet science is really going very strongly ahead at this point of time, and we have detected a large number of exoplanets which are in the habitable zone. It's at the right distance from its parent star, and possibility of having liquid water. So they are in the habitable zone. But probably double neutron star merger also plays a very significant role in the habitability, because Earth, the warmth of Earth, half of it comes from the radioactive decay of heavy material, in particular uranium and thorium, deep inside the Earth's mantle. Now, this heat allows circulation of the material beneath Earth's crust, and this circulation allows the dynamo to be operative, and for us to have a magnetic field. And now we know that the magnetic field is very important for the survival of living objects on a planet's surface, because otherwise it would be bombarded by cosmic rays, very harmful cosmic rays, and so on and so forth. So magnetic field plays a very important role by shielding us from various harmful radiation that is coming from the sky. So, if uh, the abundance, the radionuclide abundance is not optimal, then either the dynamo would not act at all, the planet would be completely cold, or it is so hot that there would be huge amount of volcanic activity, and the planet would be inhospitable. So therefore, an optimal amount of radionuclide abundance is also required for habitability, and that is again mostly going to come from a double neutron star merger. So we see that even though neutron stars look very exotic and very unusual objects, they are actually intimately tied to us as living beings. And so therefore I find that this is one aspect in which we the future investigations should go, and maybe we would find even more interesting aspects of double neutron star merger from our investigations. So, in summary, the heavy elements are produced both in supernova and binary neutron star merger. And but as I have said, binary neutron star mergers happen rarely, but they produce much larger amount of heavy elements. The likely responsible for habitability conditions, that's a very new research. One really doesn't know about very much about that. The core component of our technological advancement, which is heavily dependent on these heavy metals, these elements, these are of course dependent on this binary neutron star merger and supernova. So neutron stars, in my opinion, are the most exotic and the most exciting astrophysical objects, and young people who would take up this area of investigation in their later life, if they do, I can assure you that you would not lack for excitement and interesting findings. Thank you very much.
Thank you, Sushan, for taking us through all those dense environments and occasions of celebrating Dhanteras. And this aspect of neutron stars, responsibilities for habitability in exoplanets, that's one very interesting point you touched upon. We had a talk from Professor Sujan Sen Gupta, and again, magnetic field importance was discussed. And this is an interesting added point in that, and maybe we may have further discussions or talks on that. And actually, if you come to the tab, our studio tab, right now,
Okay.
what I will do
Should
is I
I
will
should I
flash.
should I do the stop
You keep
sharing
your
now?
you can keep it it's just in the background. If you will
Okay.
come to
Okay.
the studio tab, I will
Studio.
flash, and this is also to those watching. You can put in. There was one very
Which
early
is the
on. There was a
studio
question,
tab?
yeah.
Which is the studio
Where you
tab?
can see me in the studio, where you can in
Yeah,
the
yeah,
tab.
yeah, 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 yeah,
Yeah,
yeah.
yeah.
I am
If you are
able to
there,
see.
yeah.
Yeah,
I'm flashing the questions there.
yeah.
And so right now, this was much earlier on when you were talking about
Hmm.
artificial creation of elements. This question was
Hmm.
there.
Hmm.
Are you able to read that?
Yeah,
Arindam
there are,
has this
yeah,
question.
yeah. There are some states of matter which exist in different condition of pressure, temperature. Are there any known artificially created environment where these unstable nuclei can exist or be relatively stable? Yeah, of course. I mean, artificial environments are created so that these artificial elements can be created. I mean, they are stable at least for some amount of time. Otherwise, you would not be able to say that these have been created. But of course, these environments are created just to observe and study them. And in terrestrial conditions, these are not stable.
This was actually my question only. Heavy element detection in kilonova event. There must have been some more detections
Yeah,
later.
yeah, there have been some detections. The strontium was the first one, and that kind of confirmed that there have been heavy element detection. Later on, other detections have happened,
Huh.
and the
And
work is going on. Yes.
huh, huh. And you were saying something about expectations for clumpiness in
Yeah.
the heavy element abundances.
Yeah.
Could you kind of maybe
I mean, this is a
elaborate a bit more?
conjecture. This is a conjecture, and there isn't yet any sort of detailed study on that. People expect that because these events are rare, and the region of space in which this happens, they spew out so much of heavy material in one particular region. So then there will be some clumpiness, but how much would be retained after a certain amount of time, and whether we would be able to see a particular signature of that is not yet clear now.
Okay. If there are any further questions, those of you who are there, you could put it in text, or later on, you could put it as comments on the YouTube link of the talk. And Sushan, I'm hoping that perhaps at a later stage, if you could have a follow up for any possible small quantitative exploration which students could do related to any of the concepts that you have talked about, we could have a follow up of that at some time, maybe a couple of weeks, few weeks later or so, so
Okay.
that some of the topics that you talked about, any small
Hmm.
quantitative exploration which
Hmm.
would be possible for
Okay.
the participants to take up.
Hmm. Hmm.
So I am ending the. There is a small lag between people typing on YouTube and it coming into the studio. I hope I've not missed any questions. But if they are missed, then we will try and get them answered on YouTube directly. So I
Hmm.
will end the broadcast here now. Many thanks, Sushan, for
Most welcome.
taking us through this, and we hope to have you with us in Astro Adda as we continue.